In this video, I will show you how you can use COMSOL Multiphysics to simulate Joule heating. I will be using radiofrequency ablation treatment, which utilizes the principle of Joule heating as an example to illustrate the steps. Before we get into the steps in COMSOL Multiphysics, let's look at some definition as well as some explanation on radiofrequency ablation to facilitate our understanding of the simulation process. Joule heating is basically resistive heating. It is simply a process by which heat is produced when an electric current flows through a conductor. An example would be how a copper wire will heat up when you pass an electrical current through the wire. Joule heating involves the conversion of kinetic energy into thermal energy when charge carriers accelerate along the electric field. In radiofrequency ablation, we apply the principle of Joule heating to destroy the cancer tissue. Basically, electric current is allowed to flow into the tissue, where the same resistive heating process will cause the tissue temperature to elevate, and when it elevates beyond a certain threshold, thermal damage is induced to destroy the cancer tissue. In a typical radiofrequency ablation treatment, the patient is usually lying flat. The needle, which we call the RF probe or the electrode, is inserted into the target tissue. So this would act as your positive electrode. A grounding pad is placed at the back of the thigh, and this grounding pad basically completes your circuit. So electrical current flows from the active part of the electrode through the grounding pad, and the flow of this electric current basically induces thermal damage via the principles of Joule heating to destroy your cancer tissue. So to illustrate how we actually simulate Joule heating, the primary focus would be on the target tissue, which is our tumor here. So we are not going to model the entire human body. Instead, we are going to truncate it to the target region, which is the tumor tissue that we want to ablate. So in a typical radiofrequency ablation, we have our active electrode that consists of the active part and the insulated shaft. So the active part is where electrical current actually flows out. So if you look at this sketch over here, the red region is the region where electric current actually flows out. The shaft, which is in black, is electrically and usually thermally insulated, so there will be no electrical current flow through the surface of this shaft here. The other thing to note is that this RF probe or electrode is usually internally cooled. So when I say internally cooled, it means that there's a cooling mechanism inside the probe that can be illustrated by this figure over here. So we have a coolant that flows at the internal lumen of the probe. It flows out from the tip, and the flow in the outer lumen will actually induce some internal cooling to help cool the surrounding tissue to prevent carbonization. Now, the equations that we will be solving in this simulation would be the Maxwell equation for electrostatics. So this is a simplification of our Maxwell equation in the limit of the electromagnetic wave frequency that is involved in RFA. So here we have the Laplace equation where you have the gradient or the del dot of your sigma. So sigma is your electric conductivity, dot with the gradient of the electric potential is equals to 0. So sigma is electric conductivity, phi here is your electric potential. The Maxwell equation for electrostatics will describe the electric potential distribution across your tissue domain. To model the increase in temperature, we will be using the bioheat equation. So the bioheat equation is given by this term over here. It is different from your typical heat conduction equation because it is differentiated by the presence of this blood perfusion term. So this form of the bioheat equation is given by the Penny's bioheat equation. And you can see in this bioheat equation, we have a volumetric heat source known as QRFA. So QRFA here is the volumetric Joule heat that is produced when you have resistive heating in your tissue. And this Joule heat can be estimated provided that you know the electric potential gradient across the tissue domain. So the volumetric Joule heat is actually given by this expression that you see over here. Now, when we actually model the RFA process, especially for the treatment of cancer tissue, there are a few temperature-dependent material properties that we have to take into account. The first one would be the heat capacity, or rho times C. So I'll get into this later on. We'll look at the next two, which is K. So what is K here? K refers to the thermal conductivity. And in biological tissues, thermal conductivity has been shown to increase with temperature. And because we are dealing with a process that elevates the tissue temperature, we have to take into account the elevation in the thermal conductivity with temperature, which in this example, I will be using this expression that is shown here. The other thing to take into account is actually sigma. As I've stated before, sigma is the electrical conductivity of the tissue, and studies have also shown that the electrical conductivity of the tissue increases with temperature. This means that we will have to take into account the variation of sigma with temperature, and for this example, I'll be using this equation over here. The heat capacity term that you see here is actually included, or the variation with temperature is actually due to phase change effect when the temperature increases beyond the boiling point. So during RFA, there is a chance that the temperature elevation is so high that the tissue temperature will exceed 100 degrees Celsius, or the boiling point for water. This will cause the water inside the tissue to vaporize, and the vaporization process induces a latent heat effect that must be taken into account if we are to simulate the thermal process correctly. Omega here that you see on the right is the blood perfusion term. So the blood perfusion actually varies depending on the tissue state. So if the tissue is completely damaged, there will not be any blood perfusion, but if the tissue has not been damaged, we will assume that there is perfusion. In this particular example, I will not take into account the damage-dependent material properties. I will leave that in a subsequent video. But in this particular video, we will be looking at how to implement these temperature-dependent material properties in COMSOL Multiphysics. So the aim of this particular video is to show you how we can set up piecewise functions in COMSOL Multiphysics, how we actually model thermal effects due to phase change without using the phase change module in COMSOL Multiphysics. We'll learn how to implement temperature-dependent material properties. We'll learn how to set up heat sources, and we will be exploring time-dependent simulations. So if you want more information on radiofrequency ablation as well as how we actually model the radiofrequency ablation process here, you may actually look at these two papers, and you can actually read them to get more information to help you understand what we are going to go through next in this video. To start off with simulating radiofrequency ablation treatment, once you have your COMSOL window open, we're going to click on Model Wizard, and under our space dimension, we are going to choose 2D axisymmetry. The reason we are doing 2D axisymmetry is because we are not going to model the entire human body, simply because the ablation zone during RFA is highly localized to the target tissue, which is a tumor domain. In this case, if our tumor domain is assumed to be spherical, then there will be axisymmetrical properties that we can actually utilize to reduce our three-dimensional problem into one that is two-dimensional. Hence, in this case, we are going to choose 2D axisymmetry so that the computational resources that we use is going to be small. Now, whether you use 2D axisymmetry or whether you use 3D, you will have to look at the problem that you have, and you will have to decide if a 2D axisymmetry approximation applies in your particular problem. However, in terms of setting up the physics to solve radiofrequency ablation treatment, the steps on whether you do it in 3D or 2D axisymmetry, they will remain the same. I'm going to select on 2D axisymmetry, and you are then prompted to select the physics that you want. COMSOL already has an inbuilt Joule heating interface that you can actually use to model Joule heating. So that will be parked under your heat transfer physics, and if you look at the bottom here, you have this electromagnetic heating. This electromagnetic heating comes with two modules. You have Joule heating and induction heating. Since RFA is a Joule heating process, we're going to click on Joule heating, and here you can see the description of Joule heating in COMSOL Multiphysics, which would apply to the problem that we have over here. Once you add the Joule heating module into your physics interface, you can see that there are two physics that appear here. You have your electric currents and you have your heat transfer in solid. The reason that there are two physics in your interface is because in a radiofrequency ablation treatment, it involves the coupling of two different phenomena. The first one is your electric potential distribution, which is solved using the Maxwell equations based on the electrostatic assumption. And we have the heat transfer process, which governs the temperature rise during RFA. As such, this is a multiphysics problem that involves the coupling of electrical current flow as well as heat transfer. In addition to these two, you can also see a multiphysics tab that appears here. So this multiphysics already couples your electric current as well as your heat transfer through these three entry that you see over here. If you use the Joule heating module that is available in COMSOL, then you don't really have to worry much on how you should couple the electrical current physics to your heat transfer physics. The other thing that I want to state here is that we are using heat transfer in solids rather than heat transfer in fluids, although we recognize that the human tissue is 70% water. The reason why we are using heat transfer in solid is because we are making the assumption that the water or the interstitial fluid inside the tissue will remain stationary during the RFA process, such that the only mode of heat transfer in the tissue during RFA is by conduction. So in this case, we can use heat transfer in solids to model the heat transfer process. You may also note that there is a bioheat transfer module here. However, I'm not going to use this bioheat transfer module in this video, simply because some of you may not have this module in your heat transfer section over here. If you're using the COMSOL Multiphysics core package, you will not see bioheat transfer. However, I will show you how you can actually add the blood perfusion term into your heat transfer in solids to replicate the bioheat transfer module that you see over here. When you're done selecting the physics, you can go to study, and here we are going to select time dependent because RFA is a time dependent process. We are heating the tissue over a certain duration and we are going to monitor the temperature increase with respect to time. So in this case, we're going to select on time dependent, and when we're done, we're going to click on done, and this will bring us to the workspace of COMSOL Multiphysics. If you have watched my earlier video, then you will recall that the first thing that we have to do when we set up our COMSOL simulation is to enter the parameters. So for radio frequency ablation, the parameters that we want are basically the parameters that relate to the domain that we have. They're the parameters that relate to the equations that we have, as well as the boundary conditions. So in this video, I will not spend the time listing down all these parameters. Instead, what I'm going to do is I'm going to load it from a predefined file. If I click on parameters, then you get the parameter table here. What I'm going to do is I'm going to load it from my file, and you can see that here I have this this text editor file that is called RFA material properties. If I open this, you'll see that this file contains all the material parameters that I will be using for my RFA simulation. I may not use all of them here, but whatever I need for this particular example would be listed down here. If you want to know what are the values and what are the description of the parameters that I will be using in my RFA simulation, you can refer to the information that I have shown to you in the early part of this video. So if you look at any one of these two papers, there will be some tables that show you the material parameters that we use. For example, this first paper here is actually this paper that I'm showing to you. Okay, so this is published in 2019, and if you go down to page number 16, you can see that there is a table that lists down all the values for all the material properties that I will be using for my RFA simulation. So you can try to get hold of this paper and try and look at the values there. Going back to the COMSOL model, what I'm going to do is I'm going to load this file, and you can see that all the material properties are now listed in your parameters here. And what I've done is I also list down the description for each parameter. The next thing that we're going to do is we're going to build the geometry. So to build the geometry, we have a very simple geometry here, which is basically a semicircle when we do it into the axisymmetry, and a rectangular domain with a sharp tip at the end. So we'll start off by building the tissue domain. So what I'm going to do is I'm going to go to circle. Here I am going to put in the radius of the domain that I have. So if I go to parameters, you can see that the domain radius is known as R tissue. Of course, if you're going to call it something else, then you can use your own name for the parameter. So in my case, I have R tissue. And I'm going to change the sector angle to 180 because I am going to, I'm modeling it into the axisymmetry. And I'm going to apply a rotation angle of -90 so that it is in the positive R domain. All right. Next, we're going to add in the RF probe or the electrode. So here I will add my rectangle. My rectangle width would be similar to the radius of my probe. So the radius of my probe is called R probe. And the height, so I'm going to model first the active region, which is this active part over here. So I know that the height of my active region is known as L active, and I'm going to shift it such that the center of the active region is at the center of my coordinate system. So here you can see I already have my active part of my RF probe. I'm going to now add the shaft at the end. So what I'm going to do is I'm going to again add in a rectangle. So right now I will have the same radius, which is my probe radius, and the height would be the shaft length that I have. Okay, so this is going to be shifted down as well. So when I click on build selector, then essentially what I have is I have my rectangular domain that goes all the way outside of my tissue domain. So the last thing that I want to do is I'm going to add in the pointy tip at the end here. So this can be easily done by using a Bezier polygon option. So what I'll do is I'll add a triangular polygon here that replicates the pointy tip of your RF probe. So I'll go to, I'll add linear here. So this will actually require you to input the coordinates of the 3 points that you have. So the first point would be at -0.01. R will be equals to 0. And so what you'll do is we'll have R to be equals to 0. This will be at -L active over 2. And then the second point here would be the next point in my triangular domain. So I'm just going to key in the values, and I hope you will be able to follow what is going on here. Okay, so the second line that I add, it will be another linear line, which is another straight line. So right now I'm going to move it downwards. So here I will have -L tip. So L tip is already defined in my parameters, which defines the length of this pointy tip. And I'm going to add another line to basically close my domain. So in this case, what I have is actually have this line that goes down here, and then it has to go back up to the same point. So in this case, R will go back to 0, and this will go back to L active over 2. And you can see that this is actually not the same as what I want, and the reason for that is because in the second line here, this should go down to 0. All right, because we are going from this point to the right, we are going down, so our probe will be 0 before we go back up. So once I change this back to 0, and I click on build selected, then I'll get the pointy tip that I have. Okay, so what we're going to do next is we are going to cut out this probe domain from our tissue. Because we are only simulating the process that takes place inside the tissue, we are not interested in this probe domain. What we want to do is we want to cut this out. So we can do that by going to Boolean and partition. We're going to choose difference. So in my objects to add, I'm going to add my tissue domain. In my objects to subtract, I'm going to choose the 3 probe domain that I have constructed. So I have the tip, I have the active part, and I have the shaft. If I click on build selected, then what you see is you have your spherical tissue domain, and you have this region here that is represented by the probe. If I click on select boundaries, then you can see that there are these points at the end that define your probe. So this point, from this point all the way to the tip, that defines your active part, and from this point to the end of the tissue domain, that would be the shaft. So when you're done, as I've said, what you do is you go to form union, you build, and this will become the tissue domain that we are going to work with in our RFA simulation. Next, we are going to set up the material properties that we need to carry out our simulation. The material properties that we want are basically the values or the expressions for sigma, rho, c, k, and all of these that we have over here. As I've shown in the earlier part, these material properties are basically temperature dependent. So before we can actually set up the material properties here, what we need to do is we need to set up the functions that is needed for us to describe these temperature dependent functions here. So this can be done by going to component 1, which is the component that we have here, and we are going to add the functions that we have under the definitions here. So this can be done either by right-clicking on definitions and choose functions, or you can go to definitions in the ribbon tab and select the functions that you want under this first or this second column over here. So for me, I always prefer to go to definitions here and right-click. And if we are going to set up the functions, you go move your cursor to this function, and then you see this range of different functions that COMSOL has. And what you need to do here is to select the function that can be used to describe the temperature dependent equations that we have. So we'll start off by looking at the heat capacity method. So this heat capacity, as you can see, it basically contains 3 terms that depends on the range of temperature that you have. So if T is less than TL, so TL is a threshold or the lower threshold for your phase change temperature, the value of rho C would just take the baseline value. However, when your temperature is between TL and TU, TU being the upper range of phase change temperature, you have this expression, and when T is greater than TU, you have the vaporization or the heat capacity of vapor itself. So this function is essentially a piecewise function, because for every range of temperature, you have a particular function. So it is a piecewise function, meaning that to set it up, we are going to go to functions and we are going to choose piecewise function. Okay, so with this piecewise function, so what you can do here is you can name the function that you want. So here I can call it heat capacity, and you can see the name of the function changes to heat capacity. So the label here does not do anything to your function. It is just a name that you're going to give to your function so that you can refer to it later on. The function name itself is the function that you are going to call in COMSOL. So by default, it is called PW1, which is piecewise function 1. However, you can also change this, but when you change this, then the name of the function itself will change. So you have to make sure that when you call the function to describe the temperature dependence, you're actually using the correct function name that you have given. So here, let's say I'll call it rho times c, and I'll call it FUNC or rho c function. Now, moving on, you have argument. So argument is actually the parameter that your function is dependent on. So in our case, this function here is dependent on your temperature T. So your argument right now is your temperature. So here I'm going to call it T. I will get into this two later on. Okay. So what you're going to put into the table of intervals here are basically the right hand side function that you have. So here you can see between T and TL, oh sorry, when T is less than TL, you have rho times C. So what we are going to have is, because we are modeling radiofrequency ablation treatment of cancer, so we'll assume that the lowest temperature that the tissue can have is at body temperature. So we'll call it T body. The reason why I'm calling it T body is because in my parameters, I have already defined a parameter known as T body, which is at 37 degrees Celsius. Okay, so this T body comes from my input and it did not come from a built-in parameter in COMSOL. So from T body until TL, so I'm going to put in TL, and again, if you're wondering why is it TL, that is because I have already defined my TL, which is a lower range of phase change temperature, which is 99 degrees. Okay, so from T body, which is 37 degrees, to TL, I will have a expression that is given by rho times C. So here, my rho is defined in the parameter as rho tissue, and my C is defined in the parameter as C tissue. Okay, the second expression is between TL and TU. So in my interval, I will have TL as the start, and then I will have TU at the end. Okay, so whatever I put into the expression would basically be this expression over here. So I will have 0.5. So what I'm going to do is I'm going to copy and paste that particular function because I already have a model set up here. So what I have is I will have this thing here, which I will just put it in. All right. So if you're going to build your model from scratch, so whatever you put in from here would be whatever piecewise function that you have over here. Okay. And finally, from TU, you can see in our function, this is T or temperature greater than TU. For our model here, we need to specify an end temperature. So here I'm going to put in TU plus 5, and on the right hand side I have the heat capacity for vapor. So heat capacity for vapor would, so this would be TU plus 5. Heat capacity for vapor, which I have already defined here, is given by rho C underscore vapor. Okay, so here I will just call it rho C underscore vapor. Now, the other two inputs that you need are basically the units for your arguments and your function. So the unit for your argument in this case is temperature. So the unit for the argument would be Kelvin, we're dealing with SI unit. And the function that we have would be the unit of the output function. So in this case, for heat capacity, it is Joule per meter cube Kelvin, but which I'll explain later on. What we're going to do is we're going to set it first as Joule per kilogram Kelvin. So I'll explain why I did not put it as Joule per meter cube Kelvin once we get into the materials here. Now, once you're done inputting the function that you have for your heat capacity function here, you can always try to plot it out to see what the function looks like. Okay, so it will always plot from T body, the start temperature, to the end. Now, I told you that I'll get back to these two inputs earlier. Extrapolation in this case means that for any values of temperature that goes below T body and any value of temperature that goes beyond TU plus 5, what we're going to do is we're going to perform an extrapolation, and you have the choice of using a constant extrapolation, no extrapolation, meaning that the function will terminate at T body and TU plus 5. You can use nearest function and so on. In our case, we are just going to use a constant extrapolation, meaning that beyond below 310 Kelvin or body temperature, it will always have the same value of rho C. Beyond Tu plus 5, Tu is the upper range of temperature for phase change or vaporization. Any value beyond Tu, it will be constant as well. Okay, so that is what it means by extrapolation. Smoothing basically allows you to perform some smoothing in your function between the changes in your interval. So by default, it is no smoothing. If you change this to first order smoothing, you can change the transition zone. For example, if I plot this, you can see there's actually a smoothing that is involved that allows a more gradual gradient when it comes to the change in your parameters. In my case here, I'm not going to allow any smoothing, so I'll just choose no smoothing, and here you can see what the function will look like. Now I'm going to repeat the other functions, which is the thermal conductivity and the electrical conductivity. The procedures are the same. I'll go to function, I'll go to piecewise function. Here I'm going to choose the I'm going to name it thermal conductivity, and as my function name, to be more intuitive, let's say I call it thermal conductivity, thcon, and I'll call it function. Okay, so for my argument, again, thermal conductivity is a function of temperature, so this becomes T. And whatever we key in here would be the function that we have for our thermal conductivity. So here we only have two expressions, for T less than or equals to Tu and for T greater than Tu. So here I'll start again from T body to Tu, and what I have would be K naught, which is the thermal conductivity at baseline, plus delta K times T minus T reference. So again, I have this model set up somewhere, so rather than key in this, let me just copy this and place them here. So here you can see you have the thermal conductivity of tissue, which is your K naught, and then I have my delta of thcon, which is actually just this delta K, and then I have T minus T body. T body here is actually my reference temperature, which is the temperature at body level, so that will be 37 degrees. Okay, so now we have Tu and for the second range, and because we're using constant extrapolation, we can just choose Tu plus any value. So in this case, I'll just put 5, and whatever I put in would be the second row in this function here. So you have K naught plus delta K Tu minus T ref. So I will have K naught plus delta K. So here you would have Tu minus T body. Okay. The other thing that you need to put in is actually your units. So arguments, again, is temperature for Kelvin, and for function, because we're dealing with thermal conductivity, the unit for thermal conductivity is watts per meter Kelvin. Watts per meter Kelvin. Again, you can also plot this to see how it looks like. So here you can see the thermal conductivity basically increases linearly with temperature. Lastly, we'll have our sigma function, which is the electrical conductivity. So here I'm going to name my function electrical conductivity, and for the function name, I'll just call it sigma func. So it's up to you what function name that you want to use, but as long as you remember what it is and make sure you call the correct function, then the thing should work fine. As always, I will have T here as my temperature because it is a function of temperature. So again, we're going to do the same thing, which is T body up to Tu. Sorry, I believe this is TL, and the first function that we have is the electrical conductivity at baseline multiplied by this exponential here. So for for tissue electrical conductivity, I believe I call it sick tissue, so we can always check by going back to the parameters, and yep, so sigma tissue or sick tissue here is the electrical conductivity of your liver. Okay, so you multiply this by the 0.015 times exponential of T minus TL. So whatever function that I have here is just the right hand side of this first row. sorry, it's Tref. So my reference temperature is my body temperature, and this is what you have. Okay, so the second row, we have T between TL and TU. So what we have here is 2.5345 times sigma naught. Sorry, this is TU. And then from TU to TU plus 5, I have this expression here. So now I have TU plus 5. And here I'm going to key in the expression that I have for the third row. Let's just have a quick check. Minus 0.5018. And you have T minus TU. Okay, and finally for the last row, you have T greater than TU plus 5. So you have TU plus 5 to TU plus 10. And here we have 0.02535 times 6 tissue. Oops. Sorry about that. 25345 times 6 tissue. Okay, so the 4 lines that you see under the function here represents the 4 lines that you have on your piecewise function. So, okay, I've seen a mistake that I've made. So in the first line, we're supposed to have sigma naught times exponential times 0.015. What I have here instead is this. So I'm going to make the correction here first before we proceed. Alright, so we have our 4 piecewise function to describe the electrical conductivity. We can sub in our units, which for electrical conductivity is Siemens per meter, and again arguments is in terms of Kelvin. Alright, so we have now the 3 temperature dependent functions, which means now we can proceed on to prescribing our material properties. So in this case, I'm going to add in a blank material simply because COMSOL does not have the materials that I need for the particular tissue that I'm modeling here. For electrical conductivity, because electrical conductivity is a function of temperature, so what we are going to do is, for electrical conductivity, since we know the sigma, the function name is called sigma func, and we know that sigma function is a function of temperature. So this means under your material, under your electrical conductivity, we are going to key in the name of our function, which is sigma func, and because it is a function of temperature, we are going to write it this way. Okay, so let me expand this to show you what I've written. So what I've written is I've written it as sigma func as a function of temperature. Okay, so the next thing that I want is the relative permittivity, which has a value of 1. So I just put in 1 here. For thermal conductivity, I'm going to use the function that I have. So I'll have thcon underscore function. Again, because it's a function of temperature, I'm going to put in the brackets, capital T. Okay. Now here comes the density and heat capacity. If you recall what I've shown you earlier, this function basically describes the rho times C, which is the heat, product of density and specific heat. In COMSOL, we are required to key in the values for density and heat capacity. So in this case, because my expression has been written in terms of heat capacity, i.e. rho times C, what I'm going to do is I'm going to set the density to 1, alright? And for the value of Cp here, I'm going to put in the function of the heat capacity. So I have rho C, FUNC as a function of temperature. Now, if you look at heat capacity at constant pressure, the unit here is Joule per kilograms Kelvin. This is also the reason why I set this as Joule per kilogram Kelvin. If I'm to set this as Joule per meter cubes Kelvin, which would be which would be the exact unit for rho times C, then I will get a warning message here that says that the unit does not match. It doesn't really affect the solution, but if you do not want to see the warning message, then one way to overcome that is to force the unit here to be Joule per kilogram Kelvin, which does not reflect the actual unit for rho times C, but as long as we are aware of what we are doing, and we know that this is done solely to eliminate the warning message that we see over here, then that is okay. After setting up the materials, what we can do then is we can set up the physics of our problem. So under electric currents here, you can see that this is the equation that we're solving. So you can work out this equation to be the same as the equation that we're going to solve for our radio frequency ablation problem, which is the Maxwell equation for electrostatics. If you go to dependent variables, you can see that the electric potential is given by capital V, otherwise also known as voltage. Everything here by default should be sufficient because everything is, every material properties has been described in the material step, so there's nothing that needs to be changed over here. In this case, what we're going to do is we're going to apply an electrical potential to our active part of the electrode. This can be done by right-clicking on electric currents, and here we're going to choose electric potential. The reason for that is because we are going to apply a potential gradient into the tissue, and one way to do that is to apply a constant electric potential to the active part of the electrode. The active part of the electrode is the part of the electrode where electrical current will flow out. I can zoom in on this, and what I'll do is I'll select the boundary that belongs to the active part. In this case, we have the pointy tip here, and we have this part which corresponds to the active part. The applied electric potential is given by VAPP or VAP, which I have already defined in my parameters here. So in this case, I have stated it as 50 volts. And we need to apply a potential gradient. So at the outer end of this, I'm going to apply a ground condition. What is ground condition? You can always look at the equation here. The ground condition enforces the electric potential at this boundary to be 0. So the difference in the electric potential at the active part and the ground will induce a potential gradient that will allow electrical current to flow into the tissue. Next, we're going to look at heat transfer in solids. The thing that I want to point out here is to look at a dependent variable. So right now, temperature, capital T, is our dependent variable. If you go to solid 1, again, there's nothing that we need to add, alter here because all the material properties are taken from the material tab that we have already set. In addition, if you look at the equation, this is actually the equations that we are solving. And if you look at the equation that we have in COMSOL, we have identical terms. Let's see if I can move this a bit. Alright, so if you compare the equations that we have, on the left hand side you have rho times C times the change in temperature with time. We don't have any convection, so velocity here by default is 0. And then you have your conduction term, which is actually just the delta Q. In our case, it is this term over here. And you have capital Q. Whereas in our case, we have the blood perfusion term. What we need to do is we need to add this blood perfusion term to account for the heat sink effect that is present in your tissue. To do this, what we can do is we can right-click on heat transfer in solid and choose heat source. So the heat source setting table will appear. The first thing we need to do is select the domain that we want to apply our heat source. So we're going to select the domain, which is the tissue domain. And under the general source option here, before that, if you expand out the equation, you can see the input that is needed is actually Q. And we have set Q to be equals to Q naught. If you're wondering what is Q, you can always go back to the main physics and you look at the equation. Q is just the heat source term within your governing equation. what we want to do here is we want to key in this expression as a heat source. So whether this is a source or a sink actually depends on TV minus T. Okay, so in our case, we're going to key in this entire expression here into our heat source option. So what we do is we're going to go to rho blood times C blood. So these are parameters that I have already defined in my parameter table here, and they represent the rho B and CB that you see here. Okay, and for omega, which is the blood perfusion rate, we have W tissue and we have T body minus T. Again, please refer to the two references that I've shown to you earlier, i.e. these two references, for more details on this. Alright, now when you key in this, your entire expression here would represent the expression that you have from your bioheat equation. Okay, and you can see here we have a capital T. So this capital T is actually an unknown, and in our case, it is a dependent variable that we are going to solve for. That is what we do in order to add in the blood perfusion term into our heat transfer in solid. So even if you don't have the bioheat transfer module, you can still solve a bioheat transfer problem by adding this term here into your physics. Next, we are going to add in the boundary condition. If you recall from what I said earlier, the probe here is internally cooled, meaning that there is a cooling effect on the surface of the probe. We are going to model this cooling by using the Robin condition. The Robin condition basically states that the convection, there's convective cooling due to the internal cooling of the probe. In this case, we're going to choose heat flux, and we're going to zoom in here and select the active part of the probe. So this active part of the probe will experience convective cooling due to this internal cooling mechanism. Here, we're going to choose convective heat flux, and we're going to enter the values of H and the external temperature. The external temperature here is basically the far stream temperature of the coolant that flows through the flows along this RF probe here. So for the heat transfer coefficient, this has a parameter that a name that is given by Hcool, okay, and the temperature of your coolant is given by Tcool. Again, how do you calculate the value of heat transfer coefficient is available in the papers that I've listed earlier. We need another boundary condition to state at the outer boundary. In this case, we are going to set a constant temperature here at T body. Okay. One thing that I have not changed here is actually the initial value. So the initial value in a transient or time-dependent problem is critical because it physically represents the initial temperature of the problem. If we are talking about human body or treatment of human tissue, we can assume that the initial temperature would be at body temperature. So we're going to change the initial temperature here to T body. So this ends the setup of the physics for both the electric currents and heat transfer in solid. Now you can see that there's actually a multiphysics step, and the multiphysics step has already been set up for you. And this multiphysics step basically sets up your QE. If you're wondering what QE is actually QRFA that you see over here. The reason why there's a QE term or why there's a multiphysics step that appears here is because when we set up our physics or when we set up our model, we have chosen the Joule heating module from the inbuilt COMSOL function. Hence, all of this is set up for you automatically to represent Joule heating. If you were to select electric currents and heat transfer in solids manually, then you will have to set up the coupling manually yourself as well. Next, we're going to mesh our domain. Again, for this one, I'll just go to one of the predefined mesh setting that COMSOL has. In this case, I'll just select Extreme Refine. I'll click on Build All, and we have our mesh over here. Okay, so obviously you will need to do your mesh convergence study to determine the optimal mesh. Additionally, you may have to allocate finer mesh around the ablation zone to capture the thing more accurately. This video will not deal with that, so we're going to bypass that for now. And once you have sorted out the mesh, you can go to study 1, and because we're dealing with a time dependent problem, we actually need to set the time for our simulation. Here you can see the time unit is set to seconds. You can always change this to any other units depending on the problem that you have. For the input of time here, basically there are 3 values that you need to consider. So the first value in your bracket here, 0, represents the start of your simulation or start of your physical time. If your physical time starts from 0 seconds, then you're going to set this as 0. The second value is your time step, okay, and the last value is your final time. So in this syntax here, we're going to solve our problem that starts from 0 second to 1 second at an increment of 0.1 second. Okay, so for now, we are going to change our time to 300 seconds to represent 5 minutes of ablation, and the time step, we are going to choose an interval of 5 seconds. Now, here I want to point out that the second value, which is a time step, does not really represent the time step that your COMSOL will take to solve your problem. The time step that you see here is actually the interval at which COMSOL will record your results and store it into the system or into the model so that it will show you the results at this interval. The actual time step that COMSOL uses in its simulation is basically based on an adaptive algorithm. So the time step will change depending on how the solution changes. There are ways to change that to using a manual time step, but that will not be covered in this video. So I just want to point out that the 5 that you enter as a time step does not represent the time step taken by the solver. This 5 merely records the solution at every 5 seconds interval. Okay, now you have set up everything. All you need to do is go to study and click compute. Alright, so this will take a few minutes to compute. So I'm not going to do this here, but what I want to show is a model that I have ran earlier that has already completed its simulation. So here I did the same thing. I ran the simulation from 0 to 300 seconds, which is a 5 minutes ablation. And upon solving, you can actually get this range of results to basically do your post-processing analysis. So for example, you can look at the electrical potential. So you can see there's a high electric potential at the surface of your active part, and it gradually decays towards the outer boundary of your tissue. So this potential gradient induces an electrical current flow into your tissue. You can also plot the temperature distribution. So there's this option to plot it in 3D because remember you're doing axisymmetry. So COMSOL allows you to revolve the geometry to show the results in a 3-dimensional viewpoint. Do bear in mind that the simulation was still carried out in 2 dimensions. Okay, if you don't want to look at the contour plots that has been revolved from your 2-dimensional axisymmetry domain, you can also plot it in 2 dimensions here. So here you can see how the temperature changes across the tissue. So this unit is in degrees Celsius. You can see there's very high temperature at the ends of your electrode, which is typical of that of radio frequency ablation, where the electrical charges are high towards the end. The other thing to note is that the temperature along the surface here is very low. The reason this is low is because of the internal cooling that we have. So that internal cooling prevents carbonization next to the active part of the electrode. So carbonization is bad because if you have carbonization here, it will prevent the electrical current from flowing into the tissue. And if you have if you're preventing electrical current from flowing into the tissue, then what happens is you don't have any Joule heating anymore. So this concludes this video here. I hope you will find this video useful, especially in terms of the learning objectives which are listed over here. Um, while I have done the example or I've demonstrated the steps using radio frequency ablation, I believe the principle of modeling Joule heating for any other application should be similar. I also hope that if you are going to do your simulation on radio frequency ablation, you will find this particular video useful to you. Thank you.